As Anthony already mentioned, I'm going to talk about the plasma surrounding magnetars. Magnetars are basically the dream laboratories for us to study extreme electrodynamics. So these are relatively young neutron stars with super strong magnetic field. Their surface magnetic field can reach 10 to 15 Gauss, even beyond the Schwinger field limit. So what characterizes these magnetars is that they exhibit dramatic variability across the electromagnetic spectrum, especially in the X-ray and soft gamma ray range. It is believed that most of this variable emission is powered by the decay of enormous internal magnetic field of these neutron stars, as proposed by Duncan and Thomson, 1992. So that's also the reason that they coined the name magnetars, because they are powered by this internal strong magnetic field. So the general picture is that when the internal field evolves, they will build up stress on the crust of the neutron star. So the crust is kind of a solid layer of material on the surface of the neutron star, as Matt already talked in the last session. So the magnetic field builds up so strong stress on the crust, it will crack this crust and shake the field around on the crust. So this will generally produce disturbances in the field surrounding the magnetar, and the plasma around the magnetar will respond to such disturbances, and you will have twisted flux tubes of magnetic field, and you will have really strong current flowing in this plasma surrounding the magnetar. So this environment is called the magnetosphere. So all of these leads to the dissipation and emission in all kinds of wavelengths. So magnetars are basically, because of these extreme conditions, they are the main object of interest for our study in the sixth collaboration. So speaking of the transients powered by magnetars in the X-ray and gamma ray range, the activities typically appear in these three different classes. So the most common type of activity of magnetars is the short X-ray bursts. So here, I'm showing you one example of the observations by the Rossi X-ray timing explorer back in 2001. So you can see the x-axis is the time, and the y-axis is the count rate, basically the flux measured by the telescope. So the time is in units of seconds. So this is 0.1 second or so here. So these short bursts typically last in the millisecond to second range. And they have typical luminosities ranging from 10 to 36 to 10 to 43 erg per second. This is definitely the most common type of activities we have seen from magnetars. And then there are also outbursts. These are sudden flux enhancement, but they are much longer lived. The duration is about weeks to months, so that's an overall flux enhancement. That's the outbursts. Typically, when a magnetar has an outburst, there will also be very active bursts during that period. The third type of very powerful activity from magnetars are the giant flares. So these are basically sudden release of over 10 to the 44 erg of energy. So here, this is one of the examples observed so far. So this is from this magnetar SGR 1900 plus 14. It happened in 1998. So this is showing the flux detected by the Ulysses spacecraft. You can see that the initial peak is really, really bright. It lasted for less than 1 second. And then it has a long tail that lasts for several minutes. And you can even see the rotational period in this long tail. So these giant flares are so powerful that for this event and a later event as well, so they can even ionize the outer layer of the Earth's magnetosphere. So this even influenced the radio communication on the Earth itself. So this is a really energetic event. So far, we have only detected 3 giant flares from known magnetars. But there's some evidence that maybe we have seen extragalactic giant flares from magnetars. They are probably a subclass of the short gamma ray bursts. So all of these fascinating phenomena, there are lots of unanswered questions related to the microphysics behind these powerful events and their emission. So these are basically the main topics for us to study in the 6th collaboration. So recently, there are even more exciting developments in the observations that made these magnetars particularly interesting to study. This is related to fast radio bursts. Magnetars could be potential progenitors of fast radio bursts. So as we know, fast radio bursts are these mysterious millisecond duration radio bursts detected from outside of our own galaxy. So this is one of the first fast radio bursts detected, the Lorimer burst. It was detected in, it was published in about 2007. So this is a figure showing the radio signal detected from the Parkes telescope. You can see the horizontal axis is time in units of milliseconds, and the vertical axis is showing the frequency. So the detection appears as this track on this time and frequency diagram. So this is because when the radio waves propagate through the interstellar medium and intergalactic medium, it's basically propagating through a plasma, and the different frequencies of radio waves have slightly different speed. So the high frequency waves arrive slightly earlier than the low frequency waves. So they see this characteristic track. So this is called the dispersion. So that reflects the amount of plasma the wave has propagated through. And based on our knowledge of the electron density in this interstellar medium, we can deduce the distance of these objects. And many of them are actually outside of our own galaxy, pretty far away. So that gives us the conclusion that these bursts are really, really bright. So some of them can even reach total energy of 10 to the 42 ergs. So if you imagine some thermal source that is producing this kind of radiation, imagine what kind of temperature you will need to produce such a bright emission. You would need a temperature reaching 10 to the 40 Kelvin. That's obvious impossible, right? So the emission process must be coherent, meaning that many particles are emitting in phase so that they can produce this kind of really bright emission. So we know pulsars produce coherent emission, but these fast radio bursts are way more bright than the pulsar radio emission. So this is a completely different phenomena, I think. So the all-sky rate is about 10 to the, even above 10 to the 3 per sky per day. Now, thanks to the CHIME telescope in Canada, we have detected lots of these fast radio bursts. But it's still an open question of what sources actually produce these fast radio bursts. So in 2020, there is a very interesting discovery. We are very lucky that we caught a fast radio burst-like emission from a magnetar in our own galaxy. So this is the object. Its name is SGR 1935 plus 2154. So you can see here, this is the radio detection by CHIME. So this is the time, and this is the frequency. This profile has already been corrected for the dispersion, so you can just see the burst itself. There are these two components in these two bursts. And coincident with these radio bursts, We also see an X-ray burst coming at the same time from this magnetar. You can see below here is the light curve of this X-ray burst. It lasted for about 0.5 seconds. And you can see there are a few very bright spikes within this X-ray burst. And two of these spikes actually has more or less coincidence in time with these two radio bursts. The radio burst energy is about 2.2 times 10 to the 35 ergs, and the X-ray burst energy in this whole duration is about 10 to the 40 ergs. So the radio is only a small fraction in terms of energy compared to the X-ray emission. But this is really a very nice evidence showing that magnetars can probably indeed produce some of these fast radio bursts. Now, the next interesting question is, of course, how do magnetars produce these radio bursts? So that's also an active, important question that we are studying right now in the SIX collaboration. Okay, so my talk basically focuses on the magnetars, and we try to understand the physics, the plasma physics behind all these phenomena. We focus on this plasma physics in the magnetar magnetospheres, and we try to address how the microphysics affect the observational appearance of magnetars. So these are basically the two of the 6 organizational questions that we posted as the objectives of our SIX collaboration. So my talk will be touching on both of these questions. Okay, so my collaborators and I have been particularly focusing on the dynamics of plasma waves in magnetar magnetospheres. So this is an important question because we know that magnetars are basically powered by this super strong magnetic field that evolves inside the neutron star. And this evolution of this field can stress the crust and produce all these disturbances on the crust, like starquakes and so on. So when you shake the crust back and forth in many of these activities, you will be shaking the foot points of these field lines that go into the magnetosphere. So this will produce plasma waves that go into this magnetosphere. So this is basically a fundamental picture put forward by Thompson and Duncan, 1995, for magnetar bursts. So one of the main kind of plasma waves that can be launched due to these magnetar quakes is called the Alfvén waves. It's basically like waves propagating on a string. So here, the magnetic field lines are basically this string. So when you shake the foot point of these magnetic field lines, it's basically like plucking the string, and then you will have a wave propagating along this string. So these are basically the Alfvén waves. So theoretical studies have shown that when you shake this crust at typical frequencies of neutron star quakes, you can have waves transmitted into the magnetosphere. Most of the frequency of those waves will be above 1 kilohertz, probably mostly around 10 kilohertz. So that's kind of the typical Alfvén wave you will get from these star quakes. But Alfvén waves are not the single kind of plasma waves you can have in the magnetospheres of magnetars. Actually, in the highly magnetized plasma, highly magnetized means the magnetic energy density is much larger than the rest mass energy density of the plasma particles. You will have two main kinds of relatively low frequency waves. One is the Alfvén waves I just talked about, and the other is called the fast magnetosonic waves. So this is basically like a sound wave, but here it's not the pressure of the hot gas that's supporting the sound wave, but it's actually the magnetic pressure that's providing the restoration force for the sound wave. So this is the magnetosonic wave. And in the highly magnetized regime, this fast magnetosonic wave behaves very similar to electromagnetic waves that we know in typical media. So the Alfvén waves and fast waves have different polarizations. For example, if you just look at this axisymmetric magnetosphere with a dipole field, and you imagine some sort of axisymmetric disturbances, then the Alfvén waves typically have a wave magnetic field in the toroidal direction, while the fast wave have a wave magnetic field in the poloidal direction, in the poloidal plane, and the wave electric field is in the toroidal direction. So you can sort of see the polarization of the two waves are different. While Alfvén waves are confined to the field lines, fast waves are not. They do not care about the background field. They are just propagating isotropically out like spherical waves. So these are the important wave modes in the neutron star magnetospheres. So I mentioned that these are low frequency waves. So this low frequency means that it's usually much lower than the plasma frequency or any of the radio emission frequency we know. So the low frequency refers to the fact that the quakes typically inject waves at this kind of 10 kilohertz frequency range. So, but these waves eventually can have effects on the plasma, and the plasma will eventually radiate in radio and even X-ray and gamma rays at much, much higher frequencies. So now a fundamental question is, how do the energy injected in these low frequency waves eventually goes into radio and X-ray gamma ray emission? So that's kind of the question my group has been focusing on. So I will give a quick outline of the effects we have been considering so far. So I will first focus on a few important nonlinear effects of these Alfvén waves. And then, so there are two most important effects. One is nonlinear breakout of these Alfvén waves, and the other is generation of fast waves from these Alfvén waves. And then next step, I will naturally talk about the evolution of these fast waves. They can also become nonlinear and produce very interesting effects. Okay, let's jump right into that. The first process I'm going to talk about is the Alfvén wave nonlinear breakout. I think this could be a potential mechanism to produce the simultaneous X-ray and radio burst from this galactic magnetar. So to study the dynamics of these plasma waves in the neutron star magnetosphere, the first kind of approximation we will use is the so-called force-free electrodynamics. So because in this kind of environment, the magnetic energy density is much, much larger than the plasma rest mass energy density. So we can more or less neglect the kinetic energy and any inertia or thermal effects of the plasmas. So basically, it's just motion of plasmas dominated by the Lorentz force. So in such a plasma, basically you have massless charges that will carry the field around, and they need to provide the charge and the current to make sure that the net force, the Lorentz force on this plasma is zero. So that is basically the condition for this force-free electrodynamics. So what we have here is that we have Maxwell's equations governing the evolution of the fields, and the plasma needs to provide the necessary charge and current so that you have the total Lorentz force goes to zero. So that constraint basically gives you the expression for the current it's already determined from this dynamics. It has to be a function of the electromagnetic field itself. It's like a special Ohm's law. So with these equations, we can actually evolve the system in this strongly magnetized limit. We carry out simulations using a GPU-based code that solve these force-free equations. So what we do here is that we consider a neutron star that is axis symmetric with rotation axis and magnetic axis aligned. This is kind of a first step. And we imagine that starquake will twist this ring-like region back and forth, so that will shake the foot point of the field lines. And then that will launch these Alfvén waves. Okay, so let's see what happens. In this movie I'm going to show you, these are the dipole field lines. And we will have an Alfvén wave launched from the polar region from that ring. And I'm showing the toroidal magnetic field. So that's the wave magnetic field that you are going to see. So as you can see, the Alfvén wave propagates out here. And initially, it's propagating along the magnetic field. But at this point, it becomes a ballistic ejecta that just moves directly straight out of the magnetosphere. So what happened here? So we know that in the dipole magnetic field, the background field basically goes as 1 over r cubed. But the Alfvén wave that propagates on the dipole field lines, this wave magnetic field goes as 1 over r to the 3/2. As a result, this wave field, the relative amplitude wave field over background field, grows with radius as r to the 3/2. So at some point, this ratio can become larger than 1, meaning that the wave becomes nonlinear. So if the wave energy is actually larger than the magnetospherical energy outside some radius at this point where the wave becomes nonlinear, then you can disturb the whole magnetosphere. You basically push open the whole magnetosphere and results in an ejection. For Alfvén wave with an energy of about 10 to the 40 ergs, this is kind of in the energy range responsible for this galactic magnetar X-ray burst. So for such an Alfvén wave, this ejection radius is about 100 stellar radius. So you can see that when the wave becomes nonlinear and it has enough energy to push open the magnetosphere, it basically just moves out ballistically at this point. And in the equatorial region, the two hemispheres have these opposite magnetic field lines. They meet in the middle, and there's a strong current sheet where you have really strong current, and magnetic reconnection can happen in this current sheet. So what we think is that this ejecta, as it moves to large distances, it will produce a shock in this magnetar wind. And at that shock, the synchrotron maser effect could produce the coherent radio emission, as shown by Plotnikov and Sironi in their peak simulations of these shocks. And we think the X-ray emission, the simultaneous X-ray emission, could come from this magnetic reconnection in this current sheet formed near the equator behind this ejecta. So here you do have these opposite field lines meet, and you see these plasmoids that are formed due to magnetic reconnection. So a lot of X-ray emission can be produced in these regions. So we have also done 3D simulations. We did more general type of perturbation, for example, twisting this circular disk on the stellar surface. And the same physics still is true in this 3-dimensional case. As you can see, this is a movie showing the magnetic field lines and the magnetic field energy density. You can see as the wave propagates out, with enough energy, it can also become nonlinear and form an ejecta, opening up the magnetosphere. So in these 3 dimensions, we can have these ejectas that have relatively compact size in the angular range. This is showing the magnetic field in the ejecta. And the angular distribution can be relatively compact. We can also see that there is a strong current layer behind the ejector where you can have a lot of magnetic reconnection, releasing this energy of the stretched magnetic field by this ejector. Okay, so the basic implications from these simulations is that we can see that this galactic magnetar burst is just a moderate energy event. But when you have these Alfvén waves propagate on field lines that reach large distances, they can still produce ejectors that can go to the outer magnetosphere. And the radio burst may be produced by synchrotron masers at the shocks launched by this ejector. And you can also have simultaneous X-ray bursts produced by dissipation in these current sheets. Okay, that's for the Alfvén waves that have enough energy to break out from the magnetosphere. Oh, question?
The decaying X-ray emission as the current sheet reconnects vary with time?
Yeah, that's a good question. So here, I think from the simulation, we mostly concentrated on these very sharp peaks in the X-ray burst spectrum. So when you see the X-ray light curve, you can see a few peaks corresponding to this radio emission. So what we saw is that in these current sheets, especially the parts very close to the ejector, they are moving relativistically with the ejector, and you see the boosted emission. And you do find very sharp peaks due to this boosted emission. I think the longer tail probably depends on how this magnetosphere eventually relaxes. So that's something we haven't really characterized very well yet. Sorry. Yeah, I think that's an additional process. Yeah. Question there?
The X-ray and the radio in this process for the radiation?
Yeah, that's a really good question. I think for this kind of particular process, this ejector we've looked at, I think the X-ray beaming is determined by this emission from these current sheets. If it's moving relativistically, then it's beamed in the direction of motion. And for the radio, that depends on the shocks that eventually forms. So this is kind of the energy distribution in the angular range. So you could probably form a really large area in terms of angle for the shock. So here, I do think that this beaming is more or less consistent. So the radio and X-rays, but it definitely needs some more detailed study, I think. Okay, thanks for the questions. So next, what I want to mention is that even for the Alfvén waves that are just confined by the magnetosphere, they are bouncing back and forth in the magnetosphere, there can also be interesting things happening to these Alfvén waves. So this is one simulation I did in 2020, where I just still launch these Alfvén waves from this twisted ring. And now these Alfvén waves do not have enough energy to break out. They are just confined to the field lines. So on the left panel, you will see the toroidal component of the magnetic field. That shows the Alfvén waves. On the right-hand panel, you will see toroidal component of the electric field. That doesn't rise up in the Alfvén waves. So if you see something there, it's a different wave. Okay, so when I launch these waves as it propagates along the magnetic field, you can see that there's the production of a new wave mode here. There's this E phi. This is the fast magnetosonic waves. So we see that when these Alfvén waves propagate on the curved dipole magnetic field lines, you can produce fast waves from that process. This is a nonlinear process. And the fast wave has a wavelength about 1/2 of the Alfvén wavelength along the magnetic field line. So that was back then. Then my graduate student, Dominic Berlani, has looked at this process in more detail. Now he tried to follow the waves for longer duration. And what you see is that there are interesting things happening as this Alfvén wave bounce back and forth in the magnetosphere. Now you can see this relatively high frequency component of the fast wave corresponding half of the Alfvén wave wavelength. You can also see another longer trend of fast waves with much lower frequency. In fact, that wavelength, you will see in a moment, this component with much longer wavelengths, that wavelengths correspond to the bouncing time scale multiplied by c for the Alfvén waves to bounce back and forth in this magnetosphere. So we find that when the Alfvén waves bounce back and forth on these closed flux tubes, you can produce two kinds of fast waves. One is the one with relatively high frequency, which is half of the wavelength of the Alfvén waves. And you can also produce another mode whose wavelength corresponds to the bouncing time scale of the Alfvén wave on these flux tubes. We did very detailed studies, and we find that the basic physics behind the fast wave production is that when the Alfvén waves propagate along these curved field lines, they naturally source a second-order toroidal current, which acts like an antenna that can produce these electromagnetic waves. These are basically the fast waves. So this is showing the toroidal component of the current. So that's kind of the source of the fast waves. You will not get this toroidal current if you propagate along the uniform magnetic field. This is the effect due to the curved magnetic field. We did detailed scaling studies. So basically, the fast waves produced depends on the efficiency of fast wave produced depends on the Alfvén wave magnitude squared. And also, we find these two different regimes that this basically depends on the length of the whole Alfvén wave trend. So if you have a short Alfvén wave trend, it bounces back and forth. You produce dominantly that low-frequency fast wave with wavelengths corresponding to the bouncing time of the Alfvén waves. But if you have, that's basically this range. But if you have a very long Alfvén wave trend where it will intersect itself, you produce predominantly this high-frequency fast wave mode. That's this scaling relation. So with these scaling relations, we are able to tell, like in typical starquakes, what kind of fast waves you can produce. We find that, interestingly, for reasonable starquake energy, you can generate Alfvén waves and then produce fast waves, and these fast waves can become nonlinear inside the magnetosphere of the neutron star. So this is naturally the next topic I'm going to talk about. So you can see that the Alfvén waves produced from the starquakes, they can give energy to the fast waves. And the fast waves can do interesting things now. Fast waves can also probably be directly launched from the starquakes as well. So basically, all these fast waves will be on the frequency range of kilohertz. What they can do is that they can also become nonlinear in the magnetosphere. So this is kind of a illustration of what the fast wave looks like in the magnetosphere. So imagine you have this kind of dipole magnetosphere. The fast waves are just like electromagnetic waves propagating spherically outward. So the amplitude of these fast waves goes as 1/r, as we know. But the background dipole field goes as 1/r cubed. So you can see that the amplitude of the wave over the background field grows with radius. It grows as r squared. So given a typical energy of the fast waves, the wave can become nonlinear at some radius. For example, if you imagine a typical energy that would be responsible for some extragalactic fast radio bursts with luminosity about 10 to the 42 erg per second, if that's kind of the initial fast wave energy, then that fast wave can become nonlinear at about 2 times 10 to the 8 centimeters, also about 100 stellar radius. So if you look at the fast waves, their magnetic field is in the poloidal plane. Here I'm showing a fast wave on the equator. So that wave magnetic field, if it just superimpose on the background field, you can see a cancellation of the wave field with the background field. So when the wave field becomes comparable to the background field, you can cancel the background field, but you have a non-zero electric field from the wave. That will lead to E greater than B if you just imagine this is a vacuum. So in force-free, we cannot really handle this kind of E greater than B regions. So that is additional physics that we need to model. So we will have to go to the more fundamental level of the plasma description to describe the nonlinear evolution of these fast waves. Okay, so from now on, I'm going to talk about first principles kinetic simulations that we did to study these wave dynamics. So these are basically particle-in-cell simulations where it tracks self-consistently the evolution of the particle distribution and the electromagnetic field. So this will capture all these important microphysics when the fast wave becomes nonlinear. So we first did this work by using a simplified setup. We basically consider the quasi-one-dimensional setup where we imagine a background field that goes as 1 over r. It's basically a vacuum field from a line current. And then we launch a cylindrical wave outward. So in this cylindrical wave, you have the wave electric field that goes as r to the minus 1/2, but the background field goes as 1 over r. So the relative amplitude grows as r to the 1/2, so it can become nonlinear at some radius. So we used our GPU-accelerated particle-in-cell code aperture developed by Alex Chen. I'm going to show you what happens here. So if you just consider a vacuum, so these fast waves can also exist in vacuum. They are just vacuum electromagnetic waves. If you have vacuum and the field of the wave just superimpose on the background field, so the background field is decaying, you will see that in vacuum, you easily get to this point of electric field greater than magnetic field. So the blue line is the magnetic field, and the orange line is the electric field. So that's in vacuum. When you get E greater than B, in a plasma, so plasma will do things to prevent this to happen. So now let's look at what happens when you have a dense plasma. So still the same kind of waves launched from this end. And you can see that here, in vacuum, you would have E greater than B. But in a dense plasma, the plasma will deform the wave. The wave is basically deformed, and it prevents the wave to have E greater than B. And what you can see here, especially in this first half wavelength, is that you have a shock that develops right here. Here, there's a shock as well. So in every wavelength, you will have a shock develop after this waveform is deformed. So we actually derived the criterion that you can form a shock or not. So if you do not have enough plasma to deform the wave front, the waveform, you will not be able to form the shock because when you deform the waveform, you actually need to provide the current to generate the deformed field, right? If you do not have enough plasma, this will not happen. You will just more or less have evolution like in vacuum, right? You will have E greater than B. But when you have enough plasma that can deform this waveform, you will be able to form shocks at every wavelength and prevent E greater than B. And these shocks can dissipate the energy in these fast waves. So later on, Andrew, Heike has a question.
Sorry, just a quick question. Is this a fixed population of plasma, or do you have production also?
We do not have pair production. It's just pre-existing plasma, yes.
And in reality, I don't know the parameters. Do you expect any of these sort of gaps or to produce any plasma, or is it just too low voltage? Or?
So in realistic parameters, I think you will be able to produce pairs. In the magnetosphere of magnetars, it's very likely that you will be able to produce pairs if you do have E greater than B. So that's something we haven't studied yet. Yeah, that's a good question.
Yajie, aren't these kinetic Alfvén waves because you're doing big? So these are not pure shear Alfvén of the kind that you were getting out of the force-free model. You're doing PIC now, right?
Yeah, now these are peak simulations.
So they'll have finite E parallel and they're kinetic Alfvén waves which are dispersive.
So these are the fast magnetosonic waves.
You have also Alfvén waves, don't you, in the system?
So for this study, we are only having fast waves at the moment. Yeah.
Thank you.
Yeah, so just fast waves. Yeah. Yes.
The ions?
So we have a pair plasma in this simulation setup. So you will have a shock here, and there is indeed a lot of heating happening right behind the shock.
And if you keep propagating it, how far does the shock go before you absorb the energy?
Oh, that's a really good question. So it depends on the dissipation rate. So more or less, this evolution will cut out like the lower part of the magnetic field to make E always less than B. So that part is kind of erased by this process, more or less. So as you go to large distances, the lower half of the wave in this half wavelength, so every half wavelength, the lower part more or less gets erased, basically. So it's more or less half of the initial wave energy is dissipated. So we tried these kinetic simulations, and then Andrew got inspired by this process, and he carried out very detailed analytical calculation in the relativistic MHD framework to look at these shocks in more detail. What he finds is astonishingly, these shocks are really, really strong. The upstream Lorentz factor, Andrew calculated that, can be really huge. It's basically proportional to the magnetization, the background magnetization at the point where the fast wave becomes nonlinear, and it's proportional to the wavelength over the nonlinear radius as well. So in realistic Magnetar parameters, Andrew finds that the Lorentz factor upstream of this shock can reach 10 to the 5 or even 10 to the 7. So that's why he said this, that these shocks are probably the strongest shocks in the universe, and he called them the monster shocks. So these are really fascinating shocks. They can be strongly radiative because the cooling time scale after the shock is really, really short, and there's very efficient dissipation. So recently, Arno and Amir also carried out higher resolution one-dimensional particle-in-cell simulations of these monster shocks. And they showed that you can produce these precursor waves basically this coherent synchrotron emission, synchrotron maser emission at this shock front. This could be a potential mechanism to produce these coherent radio waves that could maybe account for the fast radio burst. So this turns out to be a promising process for fast radio burst as well. Right now, our group is doing fully two-dimensional global particle-in-cell simulations of these master shocks. This is still work done by our graduate student, Dominic Bernardi. I'm going to show you the movie. On the left, this is showing E over B. And on the right, this is showing the density. So this is a fully self-consistent dipole magnetosphere. You can see, so basically the plasma will prevent E from greater than B. And you can see, but here, especially near the front, you can see a little bit of E greater than B. Those are the precursor waves we also see near the equator region. And here is the density. So basically, we see the same kind of shock that forms. It's right here. You can see these stripes are basically the soliton-like structures where you see at perpendicular shock. So if we zoom in onto the region near the equator, this is a purely perpendicular shock, meaning that the magnetic field is perpendicular to the propagation direction of the shock. What you can see is very similar to our previous one-dimensional peak studies. You can see the formation of this shock, and we can even see some precursor waves in there. And we confirmed the shock formation criterion as we derived in our previous 1D studies. And yeah, you can see there are these soliton-like structures right behind the shock. That's typical for a perpendicular shock. And then, but in this global study, we are able to see the multidimensional effect. You'll be able to see that the shock, here is a blow up of this region of the shock. So the shock is basically here. These lines are these solitons where you have enhancement of the plasma density. And you can see the flow direction as the arrows here. So we see the shock develop over a range of latitudes. And at higher latitudes, the flow direction and the magnetic field direction are not really aligned. And they are also misaligned with the normal of the shock. So these are going to be oblique shocks. So we are currently still working on understanding these oblique shocks. But the one important conclusion I want to show you is that I will get to the questions in a moment. I'm going to finish this very soon. So the Lorentz factor upstream of the shock, we measured that for a range of different background magnetization and for a range of latitude as well. We find that the maximum Lorentz factor you can get upstream is indeed proportional to this background magnetization. This is a really confirmation of Andre's derivation of this monster shock Lorentz factor upstream. So I'm really impressed by this linear scaling with the sigma. You can see most of the sigma is basically saying the ratio between magnetic energy density over the plasma rest mass energy density. So you are basically converting this electromagnetic energy into this bulk flow. And this linear scaling basically means that this conversion is very, very efficient.
Yajie, what's the scale separation?
The scale separation in this kind of simulation, I think we have our simulation domain is kind of, Alex, can you mention the number?
We have a few hundred, about 100 plasma spin depths at the wavelength at the nonlinear. But that is the plasma frequency without Lorentz factor. So with Lorentz factor, it will be the separation is less smaller.
Yeah. Okay. So So yeah, I want to mention that this linear scaling also works for slightly off the equator for the oblique shock as well. OK, so I think I'm running out of time. I will just put my summaries here, and I'm